Chapter 21 Molecular Orbital Theory Section 21.3 The H2 Molecule. The Schrödinger equation of H2 in the atomic unit is H psi equals E psi. Psi is a function of two electrons, labeled 1 and 2. H consists of the kinetic energy operators for both electrons, the attraction felt by these two electrons from the two different nuclei. We have electron-electron repulsion and also nucleus-nucleus repulsion. Again, kinetic energy operators of the two electrons, attraction between the electrons and the nuclei, electron-electron repulsion, and over here, nucleus-nucleus repulsion. In general, when a system contains n-charged particles, the number of electrostatic potential energy terms is n times n minus 1 over 2. So again, for each of the n-charged particles, it feels either attraction or repulsion from the other n minus 1 charged particles. Therefore, in total, we have n times n minus 1 terms for potential energy. Why divided by 2? Because if we count the number of potential energy terms in the previous way, we double counted actually every single electrostatic term 2 times. So that's why we need to divide everything by 2. In hydrogen 2, there are 4 charged particles. So 4 charged particles each feels either attraction or repulsion from the other 3. So 4 times 3, we have 12 potential energy terms. But to remove the double counting, we need to divide this 12 by 2. We get 6 potential energy terms. Among these 6 potential energy terms, 4 are negative attraction terms, 1, 2, 3, 4, and 2 are positive repulsion terms between the 2 electrons and between the 2 nuclei. So in this diagram, we can see the repulsion between nucleus A and nucleus B, the repulsion between electron 1 and electron 2, and then finally the attraction between the 2 electrons and the 2 nuclei. Now let's look at the molecular orbital diagram of H2. It's very similar to the molecular orbital diagram for H2+. We just have one more electron in H2. The bond order of H2 is 1. The bond order of H2+ is 1/2. How do we compute the bond order? Well, it's equal to the number of bonding electrons minus the number of anti-bonding electrons divided by 2. So over here, when we form these two MOs, the 2 electrons occupy the sigma g bonding orbital. The bond order is therefore 2 minus 0 over here, and then divided by 2. We have a bond order of 1. In H2+, we have only 1 electron in the bonding orbital. Therefore, the bond order is only 1/2. What about H2-? That means we have 1 additional electron. We can only put this additional electron in here, the sigma u star anti-bonding orbital, and therefore we have 2 bonding electrons and 1 anti-bonding electron in H2-. In that case, the bond order is also 1/2. It's 2 minus 1 over 2. That's 1/2. So both H2+ and H2- have a bond order of 1/2 for different reasons. In H2+, there's only 1 bonding electron. In H2-, we have 2 bonding electrons, but also 1 anti-bonding electron. Now let's look at H2-. That means we need to put 2 electrons in the sigma u star anti-bonding orbital. It's very unstable. That's why in the real world we cannot see this H2-, with a bond order of 0. Again, the bond order should be the number of bonding electrons minus the number of anti-bonding electrons divided by 2. To weaken a bond, we can either reduce its bonding electrons or increase the number of anti-bonding electrons. The MO diagram of H2 is very similar to the MO diagram of H2+. The wave function for the 2 electrons in the H2 molecule must be antisymmetric under the exchange of the 2 electrons. So that's the biggest difference between H2 and H2+. In H2+, we have only 1 electron. We do not even have to worry about quantum mechanical postulate 6. which states that the total wave function must be anti-symmetric under the exchange of 2 electrons. In H2 plus, we don't even have 2 electrons. But in H2, we have to worry about this postulate 6. We write out the total wave function of the 2 electrons in H2. It's the normalization factor n times sigma g of electron 1, sigma g of electron 2, and then followed by a spin function alpha 1 beta 2 minus alpha 2 beta 1. You can see this sigma g1, sigma g2, this is symmetric. If I switch electron 1 with electron 2, I get the same expression. However, if you look at the spin part over here, alpha 1 beta 2 minus alpha 2 beta 1, well, the sign of this will change if I swap electrons 1 and 2. Again, under the exchange of the 2 electrons, we get psi of electron 2 and electron 1. Now we have sigma g2 times sigma g1, and then alpha 2 beta 1 minus alpha 1 beta 2. I just replaced every single 1 with 2, every single 2 with 1. Now let's compare this wave function and this wave function. N is the normalization factor. Sigma g2 goes here, sigma g1 goes here. No change in this part versus this part. But if you look at the spin part, alpha 1 beta 2 now becomes negative alpha 1 beta 2. Negative alpha 2 beta 1 now becomes positive alpha 2 beta 1. Therefore, psi of 2 1 is equal to negative psi of 1 2. The wave function is indeed anti-symmetric under the exchange of the 2 electrons. In this wave function, we noticed the spatial part is symmetric while the spin part is anti-symmetric. Now let's look at the spin of this function. When we look at this function, we can apply the s squared operator to this wave function, we get 0. We can also apply the z component spin operator to this wave function, we also get 0. And more generally, if we have a MO occupied by 2 electrons, or you can say this MO is completely occupied, the net spin is just 0. In this case, the alpha and beta completely cancel. We do not have a net spin in this case. But what if we promote one of the 2 electrons in the H2 molecule to one of the anti-bonding orbital, and then there are 4 possible microstates? We can write them out. We can have one electron in the sigma g orbital, the other electron in the sigma u star orbital. Now we can have alpha alpha, alpha beta, beta alpha, and beta beta. Well, this is just because now we have 2 electrons in the 2 different spatial orbitals. They have different spatial quantum numbers. Therefore, it's okay for them to have the same spin quantum numbers. So it's okay for them to be alpha alpha or beta beta. And also, we can have alpha beta or beta alpha. We can apply this s squared operator to alpha alpha. We will get h bar squared times s plus 1 as the eigenvalue. The result is 2h bar squared times alpha alpha. This s is equal to 1 because when you have alpha alpha, the s is actually 1. Instead of 1/2, you have 2 electrons here. What about beta beta? Same thing. We get 2h bar squared times beta beta. So really it tells you, well, the spin angular momentum is the square root of 2h bar squared. The z component of alpha alpha is h bar. The z component of beta beta is negative h bar. So the z component of alpha alpha is simply just a positive half h bar of 1 alpha, and then another positive 1/2 h bar for the other alpha. That's why we get h bar. And over here, when we look at the z component beta beta, it's just negative 1/2 h bar plus another negative 1/2 h bar. It's negative h bar in total. That's the z component. So now you can see we have alpha alpha and beta beta. They have the same magnitude of the 3-dimensional spin angular momentum, which is the square root of 2 times h bar, but they differ in the z component. One is h bar, the other is negative h bar. Neither alpha beta or beta alpha is an eigenfunction of the s squared operator. But if we do a linear combination, either alpha beta plus beta alpha or alpha beta minus beta alpha, they both are an eigenfunction of this s squared operator. We can apply this s squared operator to alpha beta plus beta alpha, we get eigenvalue 2h bar squared. So if you look at this eigenvalue 2h bar squared, 2h bar squared, 2h bar squared, they are exactly same. Now if we apply the same s squared operator to alpha beta minus beta alpha, oh well, this two actually cancel, you're gonna get 0. The z components of the angular momentum of alpha beta plus minus beta alpha, they are both 0. And over here we see a diagram of alpha beta plus minus beta alpha. Well, this is alpha beta, this is beta alpha, so really we need to mix this two. MO diagram, we have this diagram plus minus this diagram, we get alpha beta plus minus beta alpha. And this is just because of the quantum effect of electrons. Electrons are indistinguishable. When we write this alpha beta plus minus beta alpha, we cannot tell which electron is alpha, which electron is beta. When one of the two electrons in the H2 molecule is excited to the sigma u star anti-bonding orbital, there are 4 possible microstates. Alpha alpha, alpha beta, beta alpha, beta beta. We can regroup them and attribute all those 4 microstates or their linear combinations to S1 and T1 excited states. S1 means the first singlet excited state. T1 is the first triplet excited state. When we see this T1, that means we have a degeneracy of 3. When we see S1, that means we have a degeneracy of 1. And this is wave function to the S1 electronic state. Over here we have sigma g and sigma u star. So if you look at this, we have electron 1 in sigma g, electron 2 in sigma u star. Over here we have electron 2 in sigma g, electron 1 in sigma u star. We have a linear combination here. And over here the spin part is also a linear combination, alpha 1 beta 2 minus alpha 2 beta 1. So now let's analyze the spatial part of the S1 wave function. This is symmetric. If we swap 1 and 2, there's no sign change. We're gonna get the same expression. However, over here, if we switch 1 and 2, the sign will change. So we have a symmetric spatial part and a anti-symmetric spin part in the S1 excited state. Well, the T1 triplet excited state, over here we have a degeneracy of 3. That means these 3 have the same energy. Now let's look at the spatial part. They share the same spatial part. It's sigma g1, sigma u star 2 minus sigma g2 times sigma star u star 1. Over here we can see if we exchange electrons 1 and 2, the sign of the spatial part will change. We have an anti-symmetric spatial part. Therefore, the spin part must be symmetric. Over here, alpha 1 beta 2 plus alpha 2 beta 1. This is symmetric under the exchange of the 2 electrons. Also, we can exchange 1 and 2. We will still get alpha 1, alpha 2. We can exchange 1 and 2 here. Again, beta 2 times beta 1 is equal to beta 1 times beta 2. So in the T1 excited state, we have a anti-symmetric spatial part and we have a symmetric spin part. In the S1 state, we have a symmetric spatial part and a anti-symmetric spin part. Now again, we will review what is this? What is alpha beta minus beta alpha? What is alpha beta plus beta alpha? Okay, it's just like this. Let's just assume this one is electron 1, and then we have this alpha electron 1, this is beta for electron 2, but over here this is beta for electron 1, this is alpha for electron 2. Neither this or this is a eigenfunction of the S squared operator. So we'll have to think of a way to get S squared value. We just need to simply do a linear combination of these 2 different MO diagrams, either plus or minus. Both plus or minus, both linear combinations are denoted by alpha beta plus minus beta alpha, and this expression is indeed a eigenfunction of the S squared operator. So in the previous page we get the eigenvalues for alpha beta plus beta alpha. well, the corresponding eigenvalue of s squared is 2 times h bar squared. What about alpha beta minus beta alpha? Well, the eigenvalue of s squared is simply 0. Now let's look at the z components of alpha beta plus minus beta alpha. They are both 0. So if we look at this 4 wave functions again, in the S1 state we have a anti-symmetric spin part. Over here, s squared is 0, s sub z is 0. Now let's look at this 3 spin functions. The s squared value for this 3 different spin functions are exactly the same, 2 times h bar squared. What about the z component? Well, they are different. The z component for alpha 1, alpha 2 is positive h bar. The z component for beta 1, beta 2 is negative h bar. The z component for alpha 1, beta 2 plus alpha 2, beta 1 is 0.